Greetings, welcome to, well, once again, another great video. Alright, so for this one, we are looking at electric circuits, and it's a past paper problem from Mpumalanga, which was June 2025. Right, so I want to start with this one. I want us to start with this one. It was a multiple choice question before we go to the main question, right? Because some people struggle to answer these kinds or this type of questions, right? So here we are told that in these circuit diagrams below, the cells are identical, right? So which means that these cells carry, for both circuits, they carry the same amount of EMF, right? They have the same EMF, right? So if each cell on the parallel circuit has maybe 1 volt, each cell on the series circuit will also have 1 volt. So what that means in a nutshell is both batteries are the same. They use the same battery for the parallel circuit combination and the series circuit combination. So same battery, okay? That's what that means, they're identical. Now the resistance of the connecting wires as well as the internal resistance of the cells is negligible and can be ignored, right? So that means the resistance of the wires and that of the cells is so small that we can ignore it. What it means for the cells as well, or the battery overall, it means that it does not have any internal resistance. Remember that small r? Yeah, these batteries don't have that small resistance, right? So now the resistors are all identical. So what this means is if this resistor Y, has some resistance R, this other one will also have R, this one will also have R, and that one will also have R. So all of them carry the same amount of resistance. So we are also told that the power in resistor X is P. So if the power in resistor X is P, determine the power in resistor Y. Okay, so that's the question. The power here is P. Now, what is the power in resistor Y? So if you check our options, these are expressions. They're not values per se. They're not discrete values. So it means that the power in resistor Y will be sort of an expression or a comparison to the power in resistor X, right? So that's what we have. All right, so let us handle this. So now we're told that the batteries are identical, so we can assume that, and not necessarily assume, we treat it as a variable because we don't know the number or the amount of EMF that's in both batteries. So let's say it's a voltage V, right? Just the V total. We can call it V tot for V total, but V is fine. Okay, so they both have V, right? So they both have V. And then what this means is the value for our PX, let's call it PX, which is the power dissipated by that resistor X, can be calculated using V squared over R, okay? So this is still stating the formula. If I substitute what my V is for the resistor X, we know that since this is a series circuit, the voltage on each resistor will not be the same, or it can be the same if the resistors are identical, like in this case, but nonetheless the moral of the story is that the voltage will divide, right? Remember, these ones, they are voltage dividers. Series circuits are voltage dividers. So since these ones are identical, we will have half of the voltage being on resistor X and the other half going to the other resistor, which is connected series to resistor X. So if now, let's say we substitute for resistor X, we substitute 1 over V. That's our value for this guy. So we want to substitute that here, right? Because remember, this is just a formula. P is equal to V squared over R is just a formula. So now we are substituting the value of V and R as well, but R is just R. So we'll get that it is 1 over 2 V, and then we square it over R. R is just R because our resistor is simply R. So this will give us that Px, which is the power dissipated by resistor X, let's put it as a subscript, is V squared over 4R, right? So it's V squared over 4R. So this is the expression, right? Or rather, the value of the power dissipated at X is equal to V squared over 4R. That's our value, right? So now, what about, this is our P at X. P is V squared over R. What about Y? Right, let's go to Y. So if we get to Y, remember, in a parallel circuit combination, the voltage will not be divided, but it will be the same for both resistors. So that means our, so let's do this. For X, we have that P is simply 4 V squared over 4R. Now for Y, let's calculate. We know that power is V squared over R. So since V, this is a parallel combination, V will stay the same. It means for Y, the power will simply be V squared over R, right? There's no reason for me to use red. Right, so that is our power for Y. So that's Py. And this was Px. So if you notice, you will see that Px is basically 1 over 4, right? We can factor out that 1 over 4 times V squared over R, right? So it's basically 1 over 4 times V squared over R, right? What this means is, if you check our Py, you can even substitute if you want. You can say Px, which is equals to P, right? Let's leave it as P, is equals to 1 over 4 times Py, because V squared over R is Py, right? You can substitute if you want, but you can just interpret from here if you are used to that. So we can say Py is simply 4P by cross multiplying, okay? So our answer here would be D. On the other hand, you didn't necessarily have to substitute. You would be able to see that if V squared over R represents our power P, and Py is simply V squared over R, while Px is 1/4 of that, it means Py has to be 4 times, because we would have to multiply this by 4 before you can get a simple V squared over R, because the 4 would cancel that 4, then you would get V squared over R, right? So that's another way of thinking about it. Okay, so this is how you would do a question like this one. There are multiple questions like this that they're usually asked differently. So this is just one of those cases, but yes, this is how you would do this one. There's a trap that someone maybe might have fell for, which is taking current here. You can't say, for instance, if you use the current method, you'd have to calculate, you'd have to have an extra step. But one common mistake that people make is they will take I here, let's say that's my I total, then when it gets to the junction it divides into half I right? Half I. Okay, and then they say, okay, here also we get I, but now there's an issue with that, right? First of all, it won't work. You can't say the current in the parallel circuit will be the same as the current in the series circuit, so that logic won't work here. The reason for that is because the resistance or the effective resistance in the series circuits is not the same as the effective resistance in the parallel circuit, so you can't use I like that. You'd have to calculate I and then substitute it. This is assuming you wanted to use this formula I squared R. It can still work, but you'd have to find what this I is for that Y resistor, of which you can't use this simple logic here because the total current in both circuits will be different. It won't be the same. Okay, so yeah, that's one thing. So let's move to our other question. So we're saying here, all right, so let's look at to the main question. All right, so this is the main question. It was question 9. So we are given a circuit diagram. The EMF of the battery is 12 volts. And then the internal resistance of the battery is negligible. All right, so this circuit, there's no internal resistance, okay? So now we can just analyze this circuit. We see that there's a series resistor, and then we have in this parallel combination, right, we have two resistors that are in series, and both of them are then connected in parallel to this 6 ohm resistor, right? So there's two 6 ohm resistors in series, but they are both connected in parallel to the other 6 ohm resistor. And then we don't know the resistance R, okay? So that's what we don't know for now. All right, so we can start with the question. So the first question is for us to determine or define the term EMF in words. So EMF stands for electromotive force, and if we define it in words, if you remember, the formula for it in a circuit context is you would have the external voltage plus V internal, right? So what this means is basically EMF is the maximum, think of it like the maximum amount of energy that the battery can provide to the circuit, right? So that's essentially what an EMF is. It's just how much voltage or the potential difference of that battery, obviously across its terminals, right? So when no current is flowing, when the battery is just, you recently bought the battery and they tell you that this is the EMF, it's the maximum amount of voltage that this battery has, right? So you can check with your some textbooks define it slightly a bit more different, with maybe a difference in 1 or 2 words, right? But the way I would define it is that EMF is just the maximum energy provided by a battery per unit charge that passes through it, okay? So we can define EMF like that, which is the definition that I'm familiar with. And then if you have a different one or one that you prefer using, you can use that too, as long as it's acceptable. All right, so that is it. The maximum energy provided by a battery, the unit charge that passes through it. All right, so now let's look at calculating the total effective resistance between B and C. So basically this question is just asking us to find the total resistance for the parallel combination. Right, so for this one we can use, first things first, I want you to note something. So let's call this resistor 1, resistor 2, and resistor 3. Okay, R1, R2, and R3. If we want to calculate the effective or total resistance of these parallel circuits, one mistake that some people make is saying, well, 1 over Rp for this particular example, or in cases like this one, is Rp. Rp means parallel. Some people use R and then double slash, which means parallel as well. You use the one you prefer, it's okay. It's the same thing, okay? So it's either Rp or R double slash. I prefer Rp. So some people make this mistake of saying 1 over R1 plus 1 over R2 plus 1 over R3, right? In this case, we had up until R3. This would be correct if these resistors were connected like this. So this would be R3, R2, and R1. Then there's that, right? If they were connected like this, in this way, then yes, this would be very much okay, saying 1 over Rp is equals to 1 over R1, 1 over R2, and so on and so forth, right? But now there are two resistors that are in series here, and these two are parallel to the other 6 ohm resistor. So what that means is we must first combine R1 and R2 before applying this formula. Okay, so using this one would give you a wrong answer if you just use it like this. This is wrong, so let's use a proper way. So what we first do is we say, what is 6 plus 6? We combine those two resistors that are in series, we get that it's 12 ohms. So now from there we can say, because what it effectively does is it reduces the circuit to something like this. You would have a 12 ohm resistor and then a 6 ohm resistor, and these are connected in parallel. This is the point B to C, right? So you'd have that. So we know that if we have this, you are more than welcome to say Rp is equals to R1, R2, right? So R2 now, let's say this is R1, that's R2, right? Over R1 plus R2. Or you can use that one that says 1 over Rp is equals to 1 over R1 plus 1 over R2, right? Yeah, you can use that one, but it would end at R2. It wouldn't have an R3. Same as the one on the left. So R1 in our recent new diagram would be 12 ohms. Right, times the other one was 6, all of this over 12 plus 6. So then you punch this in your calculator and you find your answer, and I get 4, yes, I get 4 ohms. Okay, I get 4 ohms. So that's my total resistance for that parallel combination. Right, so we go to 9.3. When the switch is now closed, the ammeter reads 2.57 amps. Okay, that means our total current is 2.5 amps. Once we close the switch, our total current is 2.57 amps. How do I know it's our total current? Because if you trace the current, it lives this way, going there, right? It means our ammeter will read our total current, because this is still the current in total, right? All right, so that's total, that's I taught. It goes here. When it gets here, it splits. You'll have I1 going here, and then you'll have I2 going to the second branch. Then it goes and they meet again here, and they continue. That means the resistor R receives total current. All right, and then it goes back, and then the cycle repeats. All right, so the resistor R receives total current. Okay, we are sure of that. So they combine here at this junction, I1 and I2, and then to form total current again. All right, so we have that information now. So let us check how to find the question 9.3.1. We are told to find the resistance of resistor R. Right, it's always good practice to just pause the video and then check how you would do some of these questions before I do them. Right, so now if you look at it, we are told that our I total is 2.57 amps. Right, our I total is 2.57 amps. We neglect the internal resistance of the battery. This means V total is also 12 volts. Right, the one that is being supplied to the circuits. All right, so now what we can do is, right, so if we check our circuits, you can see that there is about 2 ways of doing this minimum. Right, so the first way we can go about it is, well, we know that our total current is that 2.57. All right, so we can use total current to find the total resistance in the circuit because we already know our total voltage, right? R is equal to V over I would allow us to find our total resistance. And then from that total resistance, we would subtract the resistance that we already know, which is 4 ohms for the parallel side. Because remember, we already know this entire resistance, the total resistance in that green area or whatever color that is. We already know what it is, which is 4 ohms. So we are left with only R. So if that's the case, we can find what's the total, and then we subtract that 4 ohms from the green area or from that parallel circuit combination that we see there of the 6 ohm resistors, and then we would be sure that the remaining one has to belong to R. Or you can take the longer route. What you can do is you can calculate the voltage that passes through the parallel circuit combination, right? By assuming, not assuming necessarily, but by noting that the total current, since this is a series circuit, by the way, once I calculate the effective resistance of the parallel combination, it means now I have reduced all those 3 resistors into one big resistor, which is connected in series to R. So what that means is I total here and I total there will be the same. So I can find what voltage is at the parallel combination, and then I can subtract the 12. I can subtract it from the 12, and then the remaining goes to R. Then from there, I can use R and I total to find, I can use that remaining voltage and I total to find the value of R. That's another way, but I'll choose the simplest one, which is the first one that I stated. So what we can do is, we know I tot and V tot. We can say R total, let's call it R tot, is equals to V over I, which is V tot. You don't have to write these tots. Just, you can say V over I. I'm just writing it for a mental note. And then V total is 12 over I, which is 2.57. If you punch this in your calculator, you should get 4.67 ohms, right? Now we know that our R total is equals to the resistor in R plus that parallel circuit combination resistor, which was what, 4 ohms. Let's call it RP. Right, let's call it RS plus RP, right? So, which is R plus 4, and then we have 4.67 as our total resistance. Now, if you transpose the 4, you would find that your R is 0.67 ohms. Quite a small resistance, but that is your R. Okay, I won't do the second method. You can do it as your homework, but you should get the same answer, which is 0.67. The second method will just make this video longer. And yeah, so now let's go to 9.3.2. the current through the 6 ohm resistor in the bottom branch. So they want us to find what is that current. Right, so we already know the total current, we know the total voltage, and we know that that 6 ohm resistor in the bottom branch will receive I2 according to our own annotation here. So we want to find what that I2 is. So basically what we're trying to say is, when the current splits in this parallel circuit combination, how much will go to the 6 ohm at the bottom and how much will go to these two 6 ohms at the top, which they combine to 12 ohms. Right, so what that means is essentially we have a situation like this. We have a situation like this where, so we have this situation, right? You have I total coming in here. Let's use red as usual. There's my total current coming in here, and then it splits. It gets to this junction and it splits. You have I1 going here, and then I2 going there. We're trying to find I2. Right, there's this rule we call the ratio rule, or ratio method. It depends what you call it, a rule or a method. Right, so then it emerges again as I total there. So what it says is, you can take for resistors in parallel, right? We know that the voltage is the same, right? But when we try to find current, we must find by what proportion does it divide. So by what proportion does it divide and get distributed to each of the resistors, right? So which then takes us to that ratio rule. Basically, if you take the ratio of I1 to I2, it would be the inverse of the ratio of the resistances. What that means is, you would say I1 is to I2 will be the same as R2 is to R1, right? The reason we invert them is because if you check our circuits, this is R1, right? And this is R2. So the proportion in which the current gets divided and distributed to these two resistors is dependent on how much resistance each one has. The higher the resistance, the lower the current. Why? Because current prefers to go in the direction of lower resistance, the least resistance, right? So it means now effectively the 6 ohm resistor will get more current than the 12 ohm resistor. So when we do the ratios, that's why we invert the two. So R2 is in the same side as I1, and R1 is in the same side as I2, right? But it doesn't end there. Okay, it doesn't end there. What we then do is let's first take these ratios. We are trying to find the i's, right? So what we do is we substitute now. This was step 1. If you practice long enough, you don't have to do it step by step. I'm just making sure that in case there's someone that doesn't understand the method. So R2 is our 6 ohm, and then R1 is our 12 ohm, right? So the math is different if now it is 3 resistors, 4 resistors, and so on. But the logic stays the same. The one with the least amount of resistance will get the highest ratio. The one with the most will get the lowest ratio, right? So if you check now, we have 6:12. It means the proportion will divide like this, right? In a 6:12 or 1:2, right? So that's how the current will be divided amongst these two resistors. So the way you now find the actual current, you take your ratio, this one, and you add it up. So some people, you can add up from the 6:12, or you can simplify the ratio and add from 1:2. So if you add from the 6:12, which is still fine, you can say, well, I1, we are looking for I1, right? Oh no, we are looking for I2. I2, because they said the current passing through the 6 ohm, remember? Current passing through the 6 ohm in the bottom branch. So we can say I2 is, we take the number underneath that I2, which is 12. Take this 12 here. That 12, we take that number. Right, so it's 12 over, we add these two, 6 plus 12, to get 18. Okay, let me make it black. 18, right? If we add these two to get 18, you put that 18 as your denominator. Then you multiply, because remember, you are trying to see how much of the total current will go to I2, or how much of the total current will be I2. So now you must take this ratio and multiply by the total current, which is we call it I tot. In our case, I tot. So that is 12 over 18 times 2.57. And this would give you, if I punch my calculator, 12 over 18 times 2.57, it would give you 1.71 amps. Right, so this is not the only way of calculating this thing. So the reason I'm showing you this method is because it comes in handy sometimes when you can't use the formula R is equal to V over I. Right, sometimes you can't directly use this formula. So you can use the ratio method to sort of gauge how much how much current will pass through each resistor. Right, it means the remaining is now what will go to I1, because I2 or resistor at the bottom will get 1.71 amps. That means the two resistors at the top will be the remaining, which is 2.57 minus that 1.7. So let's go for the more common way, because this question allows for that common way. So this one, we'll call it method 1. Method 1, which is the ratio method. All right, then the other one will be method 2. It can be a method 1, it can be, it doesn't matter. No one would write two methods in an exam anyway. You would just pick one of these, unless you have time to spare, which still, you don't need to do two methods. Right, so what we can do is we go there. If we go to this branch, we know that the current, not the current, the voltage for the branch, for the top branch and the bottom branch will be the same, right? Because if you think about it, if you think about it, our circuit now, after we did resistances, we have a circuit like this. Let me just draw it here. We have a we call this one a 0.67, which is a resistor R. And then if we combine this parallel circuit combination, we said we will get 4 ohms, right? And then this is now the rest of the circuits. Where is that? I won't draw the ammeter. It's not important for my demonstration right now. So that's the rest of the circuit, right? So what I'm saying is the voltage, when it comes, you will have V1 here and you will get V2 here, right? So I total will be here, I tot, but it won't divide. Only the voltage will divide, which is 12 volts. So what I'm saying is we can find the voltage for the 4 ohm resistor. And we know that if we find that voltage, it will be the same for branch 1 and branch 2, because it's the voltage that goes in that whole branch, which that whole branch has a total resistance of 4 ohms. Okay, so let's find what voltage would go there for our method 2. So what we can say is V is IR, right? I times R. Our I is the total current, which is 2.57. All of this multiplied by the resistance, which is 4. And then we get our voltage. So I get 10.28. 10.28 volts. Remember, if you leave out the units, your answer is meaningless. It might as well get a 0 because it's incomplete. It means nothing. All right, so now from here, now we can find what current passes through the bottom resistor, which is 6 ohm. So if the voltage passing through the parallel circuit combination is 10.28, we know that it will be the same for both branches. So it means now we also know that here we will get 10.28 volts, and at the top, these two resistors will get 10.28 volts as well. Right. So we are only concerned with the 6 ohm resistor for now. So at this point, we can find what current it will get. So we can say current at the 6 ohm resistor. Some people prefer writing the subscript like this, which means the current at the 6 ohm resistor would now be voltage over the resistance there. So our voltage is 10.28, and then our resistance, we said it's 6 ohms. So this gives us, it should give us the same answer as before. Yes, 1.71 amps, which is the same answer as before. We also got 1.71 this side. So you can use whichever method. By the way, this one looks longer because I was sort of teaching how the ratio method works, but in actual fact, it would only be these parts that you would write in your exam. It would only be that part, right? There's an extra step where you would have to show us where you are adding the resistances to get that 18. So basically the extra step that would be there would be to say I is, it's I2, right? You will put R1 there, and then you say R1 plus R2, then you multiply that by I total. That's the extra step, which would be the first step, right? All right, so that's it for this part of the question. Now for the last part. So the last part of this question was saying a learner connects a conducting wire with negligible resistance directly between B and C. So remember, that's C and that's B. So he connects a wire here, just like that. Let's make it red so that it's easy to see. There, he connects a wire just there, right, from this point to that point. All right, so that learner connects that wire. Okay. All right, so what would happen here is that now, since we have a wire between B and C, The current now that's flowing in the circuit will ignore all the 3 resistors that are in that parallel circuit combination. So it won't split anymore. It won't split to this branch and to the top and bottom branch. Instead, it will follow the red wire. Why? Because the red wire has no resistance. Remember, we said the wires have negligible resistance. So the red wire, the one that this learner just added, I'm calling it the red wire, but it's just a wire. In our diagram, it's red. Right, so it has little resistance. So for that reason, current will want to flow, all of the current, by the way, will want to flow in that wire. So what that does is it changes the whole circuit now. It means effectively our circuits, the new circuit will be something like this, where I can add the ammeter here. Right, so this is our new circuit. Once I add that wire there, our new circuit will be like this. If you check, it means now, because remember our R was 0.67 when we calculated it. So this R was 0.67 ohms. Right, so it means now the circuit in overall has lower resistance from 4.67 to 0.67. So more of the current will be flowing in resistor R. So if you remember, power is given, let's use current in this case, because that's what we're talking about, I squared times R. So what happens if I increase the current? Because that's what will happen once I only have one resistor here. The current flowing in that 0.67 ohm resistor will now be higher, because the entire parallel combination is gone now. All of the current is flowing towards the 0.67 resistor. Right, so what that essentially means is that the current at the 0.67 ohm resistor will now increase. So what will happen to the power if this current increases? The simple answer is it will increase, because power and current are directly proportional. Not directly proportional, but proportional. So actually it's the same thing. They are directly proportional, because if I say proportional, it's a bit vague. Right, and then it means if I increase current, power will increase. A good example, let's say resistance is 1 and I put 2 here and I square it, my resistance is 1, power will be simply 4. What happens if I increase 2 to 3? I put 3, I square it, I keep resistance the same, I will get that my new power is 9. Oh, I forgot the units, 9 watts. Right, so you see, increasing the current will make sure that the power also increases. So our answer there is increases. That's our answer. Increases. And then our reason is simple. It's basically everything I was explaining. If we add the wire here, the current will follow that wire. All current will flow through that wire, which effectively removes all these 3 6 ohm resistors. That is called short circuiting, yes. So because now the current won't go to the other resistors, it'll just flow into this wire. So as it does that, now the total resistance in the circuit decreases, because the parallel block is gone, and then because remember, the current will also increase. Why? Because if we do this, I is V over R tot, right? R tot has decreased, so therefore current will increase, right? So as current increases, it affects the power. Power also increases. So that's our reason. So that's all the reason you need. Basically, the power will increase. And how do we get to the power increasing? The total resistance of the circuit will decrease, because that adding of the wire short circuits the parallel combination, which removes about 4 ohms from the total resistance. That means now we have 0.67 ohms in the total resistance, because the 4 ohms is gone. Remember, it was initially 4.67, right? And then since we know that I is equals to V over R, so reducing the resistance effectively increases the current. So the total current increases since the total resistance has dropped. Now, as the total current increases, remember, this entire total current will be received will flow through the remaining resistor. So that means the power in that resistor will increase, because before it wasn't getting that much current flowing through it. So an increase in the current will also increase the power. Why? Because, let me say, you don't need to edit here, because P is I squared R, as I've already explained. All right, so that's it for our video today, and I'll catch you on the next one.